or good evening, everyone. Thank you for attending our webinar. The objective of this webinar is that Honeywell has observed one or more unnecessary system component removals for some of the fault codes or fault code combinations in our line maintenance manuals, which have led to one confirmed component removal or another radar system component tested at our service facilities as no fault found. This webinar and our associated service information letter will provide airline operators and business jet operators and the maintenance personnel with additional fault isolation and troubleshooting guidance using the extensive byte capabilities of the RDR-4000's RP1 weather radar processor to help reduce the number of unnecessary removals for this radar system, which will help to reduce operators' costs and flight delays. The RDR-4000 Weather Radar System is a solid-state radar. It does not contain a magnetron. It uses gallium arsenide field effect transistors in its solid-state transmitter. Unlike previous radar systems, which had a tilt control, we have a three-dimensional buffered memory which constantly updates and contains all weather data from 0 to 320 nautical miles in front of the aircraft and from 0 feet to 60,000 feet above ground level. All that weather is constantly updated and stored in memory. And instead of a tilt control, as I mentioned, it will automatically show you the relevant weather within plus or minus 4,000 feet of the altitude of your aircraft, and shows it as relevant or irrelevant weather based on the inputs from the flight management system. The system's capable, of course, of rainfall detection, turbulence associated with rainfall, and predictive wind shear. Also, some units have an enhanced turbulence feature, which can extend the turbulence range from 40 nautical miles to 60 nautical miles. And this is considered to be an X-band, the frequency of operation radar system, which is designed as a avoidance radar, not a penetration radar, but an avoidance radar. The system contains the following major components: a radar processor unit, which is the unit on the far right in the picture that is located in the electronics bay, a transmitter receiver unit, or TR1, and you can see an example of that in the middle component, which is the DA1 antenna drive unit, and at the bottom of the pedestal turned on its side, you can see a TR1 transmitter with a cable from the DA1 internal assembly attached. There's a 30-inch flat plate, either an 18-inch or a 24-inch attached to the DA1S drive unit. And then finally, on the left side, there's an optional radar control panel. The various business jets can either use in the EFIS display system a virtual radar control panel or other dedicated control panels where they can use a CP1A Honeywell radar control panel. This is the front of the RP1 radar processor unit, which is the heart of the system. It's located in the electronics bay of the aircraft in the pressurized area. And as an example, you can see the liquid crystal display, and it's showing flight leg 43. It stores up to 43 flight legs of fault data. And in this example, it's showing fault code 3049, which we'll be discussing later. And looking at the front of the unit, just below the LCD, you navigate through the LCD menu system with the two push buttons. One is for scrolling and the other one is for selecting the screen that you would like to view. and the data you like to view. Then just below that, there's an area on the left-hand side, a little plastic door labeled ATP. That's for the factory and for our service shops to connect test equipment via an Ethernet cable. And then on the right side, you'll see data load. There's a little door that covers a slot for a compact flash card. And we do have on-wing loadable service bulletin software updates. And you do that by means of inserting the compact flash card. The TR1 is the transmitter receiver unit, and that is located in the radome, mounted in the bottom portion of the DA1S antenna drive unit's pedestal. So you're looking at technically the front of the unit. On the far side, the only thing that you can see is there's a little waveguide insert, which connects to the waveguide section, very small, only a little over ½ meter in length, and that's contained in the DA1S assembly, which then attaches to the flat plate. So here on the rear of the unit, we see two connectors. The smaller top connector connects to a cable, which is part of the DA1S assembly. You don't detach it from the antenna drive. You simply disconnect it from the TR if you need to replace and install a new TR unit. Then the bottom, the big connector, which has two coaxial cable inserts in the middle, that's for the cable harness that goes through the bulkhead from the radome, through the bulkhead of the aircraft, and onto the pressurized electronics bay to the RP1 radar processor unit. We'll be talking in our discussions about a 64 megahertz clock and a 48 megahertz intermediate frequency, and that is associated with the two coaxial connectors for the two coaxial cables that are in the bundle that make the connection with this large connector. This is a close-up of the DA1S, the short stature antenna drive designed for the smaller radomes in our business and corporate jets. And you can see in the bottom, again, a little closer view of the TR1 as it's mounted, and the cable connected to the gimbal drive module to the TR1 at what is actually the top of the TR, and the either 18 or 24-inch flat plate antenna array mounted to the DA1. The communications between the TR1 and the DA1 we'll see as when we review the block diagrams is by means of an internal RS-422 communications, and that is in the middle of that large black cable that's connected to the TR1. The TR1 also supplies the voltages for the drive motors and antenna positional resolvers. Again, that power is through the black cable along with the RS-422 communications. And then finally on the right side, the gimbal drive module is the electronics. There's a very powerful microcontroller, microprocessor, and at every moment it receives attitude, pitch and roll information from the TR1, which receives its information from the RP1 in the eBay, which receives its attitude information from the guidance system in the aircraft. But every moment, the gimbal drive motor makes the corrections as necessary with the pitch and roll, like most radar systems, and then using the azimuth and elevation motors, corrects for the motion and movement of the aircraft. And of course, does the normal azimuth motion and elevation motion, not as tilt, but to fill in the three-dimensional volumetric buffer inside the RP with radar data. Now, this is the optional CP1A control panel that we typically use for business jets. And again, this is optional. You might be using a different control panel. So whether it's an actual different hardware control panel or a virtual control panel in software, the functions are very similar. So we'll quickly review those. So in the top middle of the panel, you'll see test position and normal position, like most radar systems. So you'll usually have it in the normal position. When you put it in the test position, the system only transmits for a very, very short period of time, not to endanger the flight crew or the maintenance crews outside the aircraft in any way. For much less than a second, it emits a very short burst of energy just to check the capability of the transmitter byte. And then the transmitter is turned off. We check the motion of the antenna, all the internal electronics of the control panel, if there is one, of the RP, the TR, and the DA. Everything is constantly checked. And then on your navigational display, you'll see the test pattern display to let you know everything is functioning properly. When you first apply the breaker, it is totally normal that it can take up to 60 seconds to see the display, and this is because it does take some initial time to fill the three-dimensional buffer. It's not like some of the older radars where even if there's a magnetron, after 20 or 30 seconds, it warms up, it's ready to go. It can take a little bit of time in order to completely check everything out and fill the memory buffer the first time. That's perfectly normal. Both the pilot and the first officer have their own independent controls. So the common position is the weather auto mode, where it will automatically take care of the system, and it is a completely automatic radar except for one item, and that's range. You still need to constantly change back and forth between short range and long range. That's why most operators, for instance, the pilot will maybe have the display left on the longer range and ask the first officer co-pilot to use one of the shorter ranges, like 40 or 80 nautical miles or even 20 nautical miles, so that they don't get surprised by a very quickly growing thunderstorm that might only be 30 or 40 miles from the aircraft. In order to better analyze a storm, if you sense it in the auto position, similar to older radar systems, but different. You have a manual, and on some control panels called the elevation mode. But in the manual mode, what you're actually doing, instead of tilting the antenna, because it's automatically filling the buffer, you can manually select different altitudes of data or horizontal slices through the storm. For instance, if you were flying at 45,000 feet and you wanted to look at the intense rainfall, which you know is at maybe 15 or 16,000 feet, you can use the ALT, the altitude control there on the bottom left, and select 15,000 feet. And you say, wow, look at all that rainfall down there. But then when you manually bring it back up to 45,000 feet or go to the auto mode, then you would notice that most of the weather has disappeared, or that it's showing as secondary weather with the diagonal lines, and that's completely normal. Like most radars, you do have a system gain control. So you'll normally leave that in the center position, called cal for calibrated. And you have the ability to, if there's a lot of weather activity and you only want to see the areas that are most red and yellow, then you can turn it counterclockwise to minimum and see only the most intense parts. Or if you want more sensitivity, then you can move it to the maximum position. But you should always, for the most of your flight, leave it in the cal position. And of course, the right side for the first officer operates similarly. This is a simplified block diagram of the system. The heart of the system is the RP1 radar processor in the eBay. And we need, of course, power. And in the business jets, unlike air transport, which is 115 volts AC, 400 hertz only, it depends on the aircraft. On the business side, we have radar processor part numbers that can accept 115 volts AC, or we also have a series of part numbers that can accept 28 volts DC aircraft power. We also need to interface with several different aircraft systems, which I'll be showing you some details shortly. But basically, in the business jet world, we're interfacing using either ARINC 429 digital, separate transmit and receive buses, analog, or discrete logic. Discrete logic meaning either a high impedance open or a ground or plus 28 volts to determine the logic. But many of the business jets use Ethernet connections, even especially for the radar controls and the radar displays. They're starting to use Ethernet connection now. The radar processor, once it is, you apply the breaker and it is powered itself up, it needs to supply power to the TR1. So you'll see an arrow that shows 200 volts DC. And the reason we picked a very high, relatively high voltage through the cable is so that we could draw less current. So it's a higher voltage and a lesser current. Then inside the TR1, there is a voltage converter, which then exchanges that 200 volts at a small current to a relatively usable plus 29 volts DC and a little bit larger current for its transmit and receive circuits. And then in turn, the TR1 is going to supply a 29 volts DC bias over to the DA1S drive unit for its internal GDM, gimbal drive module electronics. We need to build some communication links. So you'll see ARINC 429 transmit and receive between the RP1 and the TR1. So this is where we give it the commands to transmit or receive, what type of pulses to transmit. Are we in the weather auto mode, weather manual mode, or the map mode? Are we in the standby predictive wind shear mode? You know, what mode of operation are we in? And then the TR1 uses an RS-422 communications link between itself and the GDM module inside the antenna drive to supply things like, hey, we're supposed to be transmitting and receiving. You know, have you accomplished that? Is the antenna moving properly? Exactly where's your antenna located? And also, you need pitch and roll attitude data. So the RP1 has sent me that data. Here you are. Now I want you, GDM module, to compensate for the aircraft motion to stabilize the display. Then the TR1, as it transmits the X-band energy between 9336 and 9376 megahertz, that passes through a very short waveguide section between the TR1 and the flat plate antenna mounted on the DA1S drive unit. Now there's another form of communications that is possible between the TR1 and the RP1. Please notice on the left side, there's a coaxial cable called the 64 megahertz clock and BPSK data. BPSK means biphase shift keying. So the TR1, in order to speed up the communications process so that we're not constantly utilizing the ARINC 429 for moment-to-moment updates, things like the position of the antenna every moment in time, we modulate that 64 megahertz clock with BPSK modulation so that the RP1 can synchronize and know exactly where the antenna motion is at every moment. And the TR1 constantly updates when it transmits a pulse, that it's successfully transmitted a pulse so that the RP1 knows that the operation has successfully occurred. Now, unlike our earlier radar systems, which used a long, I mean, there were two types. If you've had a system, for instance, called that's Honeywell, a Primus 660 or Primus 880, both it's nothing new there that the transmitter and receiver unit were all in one component that was inside the radome. So in the 4000 system, we've split off the major processing and control functions as a separate radar in the eBay. Now for the major airlines for years, they used a transmitter, receiver, and processing in the eBay with a very long waveguide run to the bulkhead to the radome, which over the years causes many different issues. So that is non-existent in this system. What we've replaced it with, since we have the main processor in the electronics bay, the TR1, when it receives an incoming signal from the clouds at 9336 to 9376 megahertz, the TR1 does a down conversion to a much more manageable 48 megahertz intermediate frequency. So we call that the 48 megahertz IF cable. Then it supplies that to the RP1. Then the RP will do an analog to digital conversion of that signal, and then the magic of the digital signal processing, and then develop the video that you see on your navigational displays. And then in order to synchronize everything, the TR1's 64 megahertz clock is used as the main timing for the digital signal processing and conversion inside the RP1 radar processor unit. Very, very critical and important. And then finally on the left side, now if you have a standalone control panel, such as the Honeywell CP1A control panel, we need to supply bias to that, voltage bias, so that's plus 28 volts DC from the power supply in the RP1. And then the data as to where you've placed the controls, the elevation control, the mode of operation control, etc., that is sent using an RS-422 data bus from the control panel to the RP1. Now we're going to get into the section where we discuss the fault codes. So again, here's the RP1 processor. We've already discussed the power bias, the basic interface to the aircraft systems as far as ARINC 429, Ethernet, and analog and discrete logic. Before we begin the fault codes, please note all the various equipment that we need to interface with in a typical aircraft. We have the audio management unit because this radar speaks. If there's a wind shear event, we can announce a monitor radar display, or a wind shear, go around wind shear ahead as an example. So we need to access the sound system for that. Air data inertial and reference unit. So that's a combination of the air data system and the attitude system. We need things like the ground speed of the aircraft for our processing of turbulence. We need to know the pitch and roll of the aircraft for correcting the antenna motion as the aircraft travels. And central maintenance computer. Some of the business aircraft have a computer that we will send fault information to, so the maintenance crews can easily analyze difficulties with the system. The enhanced ground proximity warning computer, the EGPWS, whether it's a card in an EPIC system or a standalone unit like the Mark V or Mark VII, we need to coordinate efforts with the ground procs, because the ground procs will also have displays for terrain warnings, etc., and also will be giving you controlled flight into terrain warning announcements, just as the weather radar gives us predictive wind shear announcements. Flight control units, that's referring to the pilot and first office navigational range request, what range you want the display to be on. The flight management system, which is a first for our radar systems. We need to determine for our radar, when you're in the weather auto mode, the flight path of the aircraft. And also we already know the altitude window of the aircraft, so that we can just show the flight crew the relevant weather and what is irrelevant weather. Relevant weather is shown as solid on the display, and irrelevant looks like it is shadowed out with some cross bars through it. So that we're helped by the flight management system to decide that. The navigational displays, of course, we provide either the older ARINC 453 video interfaces, or for the display systems, we can provide the display through Ethernet. Predictive wind shear qualifiers, you don't want your aircraft transmitting while you're on the ground looking for wind shears, unless you're doing just prior to the takeoff roll. So we look at things like the engine oil pressure to determine when it's safe to transmit if I'm in the standby mode of operation. Radio altimeter, much like TCAS and ground procs, you need these lower altitude trip levels. The weather radar starts processing the predictive wind shear below the 2,300 foot level, and would show its announcements below 1,500 feet. And so we determine that through the radio altitude. Traffic collision avoidance system, TCAS or ACAS. Like the DGPWS, we need to coordinate audio announcements, because there's a prioritization. So that's determined between the radar, the ground procs, and the TCAS. Of course, all kinds of program straps. And then finally, EPIC radar control panel. We have inputs through the Ethernet for the EPIC systems as an option for the radar control panel instead of an actual standalone control panel. And now we'll start discussing the byte codes for the RP1.
Coming to the byte troubleshooting, a 3049 fault usually gets logged when the estimated receive power is very low for each of the pulse, and when the pulse sequence is less than 8 seconds usually. And when this occurs, the radar processor, the IF converter of the radar processor, logs a receive power bit test fault. And we would be discussing more in details on why we have separated these fault codes based on each product, like you see RP here. A 3057 is a weather radar RDSP radar receive power fault, which is also reported by RPIF converter. And for both of these fault codes, we have been seeing transmitter receiver removals. And when these transmitter receivers are received at Honeywell RNO and tested, there are most likely no fault found. So our first troubleshooting would be to test and replace the radar processor, and the second step would be to check the 48 megahertz IF coax cable, which runs from the TR to the RP1. Now in the next, we see two of the fault codes, which is a 3055 and a 3716. And if you see here, these two fault codes are getting logged together, and you need to scroll down on the RP display to see if both the fault codes are in the same flight leg. And when these two fault codes get logged together, we also see RTO removals. A 3055 gets logged when digital receiver processor detects the formatted pulse data message inactivity fault. And that means when there is no pulse data message received for 2 seconds, and the radar continues to stay on transmit mode. And a 3716 usually gets logged when RDSP, virtual ARINC 429 antenna status bus, fails monitor. And this fault will get logged, also leading to a weather inop and a PWS inop being logged on the navigational display. So for these two combination of fault codes, we always recommend the RP to be replaced first. And if the RP replacement still continues to transmit these faults, then only we would recommend a TR replacement. And we're now moving to control panel faults.
Thank you, Rosemary. The control panel again receives 28 volts DC bias from the RP. Then we send the data communications, which is the position of the control panel, controls using an RS-422 data bus. And again, I want to caution, some business aircraft will not use this control panel and will not use the RS-422 data bus for the control information. As an example, if the video system is based on Ethernet, then the controls would be supplied to the RP1 also by Ethernet. So this is for the dedicated radar control panel. And we have one fault code.
Thank you, Bob. And in irrespective of we having a control panel or even if it is optional, we still continue to log control panel faults in the RP. The control panel faults that we see here are 8001 and 3106. 8001 fault is a control panel internal failure, and it's a combination of all the detectable control panel faults. And if there is a hard failure of 8001, then the control panel would have definitely failed and it's not the RP. We would always recommend for a control panel replacement and not the radar processor. Now, a 3106 fault usually occurs when the control input operational display selection between the captain and the first officer shows a mismatch. And this fault could get logged if there is an unassigned mode that's been activated as well. Now, if only the 3106 is logged, then we recommend none of the RDR-4000 components to be removed. And only if a 3106 is logged along with an 8001 fault, which again can be scrolled down in the RP to check, then we would recommend a control panel replacement. Only and only if it's combined with an 8001 fault. We're now moving to TR faults.
Thank you. Again, the interface between the TR1 and the RP1, we know about the ARINC 429, the plus 200 volts power. I do want to speak just shortly also about some troubleshooting for the 64 megahertz clock and 48 megahertz IF coaxial cables. As Rosemary's discussing the byte codes, the question is, how do I determine whether or how can I verify that one or both of those cables is defective? And of course, like most coaxial cables, you cannot really determine it easily with a voltometer. You can only find an obvious short circuit, or if you use an extension, possibly check for opens, visual damage. But the best way of checking the cables is using the instrument called a TDR, a time domain reflectometer. And what's great about that instrument is you know the length of your coaxial cable, and it can show you almost precisely where in the cable from the distance from where you apply the signal, which is usually in the eBay. You disconnect the connector from the RP1 and inject the signal there with a disconnecting the cable at the TR1 and applying a 50 ohm dummy load, but it can point you to exactly where the damage in the cable is. And then more than likely, unless it's only at the connector itself, you would probably replace the coaxial cable. But a TDR is quite useful. And now Rosemary's going to discuss the associated fault codes between the TR1 and RP1.
Thank you, Bob. That was really useful information on the cables. And coming to specific TR faults, the first fault we see is a 3055. And we earlier saw a 3055 and the 3716 getting locked together, in which we recommended an RP removal. But a 3055, when it gets logged alone, that means in a flight leg, when you only see a 3055 fault getting logged, which is a formatted pulse data message fault, generally in transmit mode. When this fault alone gets logged, we always recommend the TR to be troubleshoot first and replaced if necessary. And if the TR replacement does not fix the issue, then as Bob suggested, we need to check the 64 megahertz clock cable from the TR to RP. Coming to 5051 and 5046, these two faults are TR down converter faults, and they're specific to TR only. So there is no other component that would have failed if these faults are logged, or even if they are combined with any other fault, we can still be sure that the TR has failed. So a 5051 fault is declared when the down converter is in calibration mode and the pin state is low, and this indicates that the IF calibration is out of its specified limits. And when in receive mode, a 5046 could get logged if the pin state is also in low, and indicating a failure of the local oscillator on the down converter board. And as I said earlier, these two faults are TR only faults. A 4001 is used to verify switching device from an open to a short on a drive assembly motor. And this could most likely occur due to a TR being faulty and not communicating with the DA. And we always recommend a TR check and replacement if necessary first, and only then move to DA troubleshooting. A 4015 fault is a TR of 422 activity check, and this is to check the RS422 activity from TR to DA. This fault could occur during cycling of 200 volts to DA, as we saw in the earlier slides, the 200 volt supply, and this again could be leading to a TR failure. And only the second troubleshooting would be the moving to a DA. We saw in the first troubleshooting slide, a 3049 alone and a 3057 alone would be an RP fault, but every time it's combined with the 5051, which is for sure a TR down converter fault, then we would always recommend a TR to be replaced.
Okay. Once again, here's the interface between the TR1 and the DA1S. Please remember we have the 29 volts DC from the TR1's internal power supply to the DA1S, which powers the internal GDM gimbal drive module of the DA. And we have the RS422 communications link and the bidirectional waveguide section, which is internal in the DA1, transmit and receive energy. And we have one associated fault code we want to address in this session for the DA1S.
Thanks, Bob. We only see one fault code here, and which is mostly due to a spurious or a nuisance occurrence, with logging a radar byte fault code 5049. And this fault may be generated during power transients, like those associated from transition of aircraft to ground power and engine shutdown. And during these power transitions, there could be a temporary loss of RS422 data communication between the receiver transmitter and the antenna drive, and which may result in Wixer inop or a Wixer fail message along with the 5049 getting logged in the RP. And this fault is generally logged for a minute or so before it gets reset or cleared by itself. We're seeing some of the operators remove the TRs when this fault is logged, but we recommend to do a self-test to confirm if only a 5049 is logged. And if that's the situation, then there is no crew action that's required for recovering radar operations. And if this fault code 5049 is continuing to get logged in several flight legs or it's permanent, only then a DA could most likely be faulty and not the TR. We are moving to 64 megahertz clock cable faults.
Thank you, Rosemary. Again, back to our TR1 to RP1 interface, we're now going to concentrate on the 64 megahertz clock. And we do have an associated failure. And what happens, the RP1 is monitoring the BPSK modulation data. And if it loses that data on the 64 megahertz clock signal, because the amplitude of the clock or the timing is completely off, then we'll log that as a failure. And Rosemary's going to discuss that now.
Yeah, thanks, Bob. We have some specific faults logged here. We would have other faults as well, but these faults are specific to 64 megahertz clock cable being faulty, and in which the 3042 is an RP, pulse data message communication fault. And if this fault occurs, we first recommend to check the 64 megahertz clock cable. And if the condition and the continuity is seems satisfactory, only then they replace the TR. We saw earlier that a 3055 is associated with several different ways of troubleshooting. You know, when it's with a 3716, it's an RP. When it's a 3055 alone, then it's a TR. But when it combines with a 3057, then it would be 64 megahertz clock that needs to be checked first and replaced if necessary. And if there is no wiring issue, only then the TR could most likely be faulty. Okay, so we're moving to ARINC 429 data faults.
Okay, thank you. And the ARINC 429, of course, I mentioned earlier that this is for the primary means of communication between the TR1 and the RP1. Also, when you have a service bulletin and it's you need to upgrade the components, you apply a compact flash card to the RP1, and then once the RP1 software has been loaded, it needs to communicate to the TR1 and load the TR1 with the new software as well. So using the ARINC 429 buses, we transmit the data to the memory of the TR1, and then one bit at a time we do what's called a checksum, and we verify that the data has been loaded correctly. Then please remember that the TR1 has RS-422 communications to the GDM module in the antenna drive unit, and it needs to do the same. The TR1 is commanded by the RP1 to load new software into the GDM card of the antenna. And if you go to the menu on the RP1, it will show you the software part numbers and revision levels on the configuration part of the menu. It'll show you the real-time status of the software part numbers of the RP1, TR1, and DA1. And now Rosemary's going to discuss some of the fault codes associated with the 429.
Thank you, Bob. For the ARINC 429 cable, we see three of the faults that we can be quite sure of an ARINC 429 failure, which is 3716, 3029, and 3032. A 3716 is logged when there is an RDSP virtual ARINC 429 antenna status bus failing to monitor, and the antenna status bus is mostly inactive, which leads to a weather inop or a PWS inop getting logged. And a 3716 would first warrant an ARINC 429 data cable check. And if the data cable continuity is satisfactory, only then the TR and then would be the RP as a troubleshooting. A 3029 is a weather radar RDSP digital receiver FPGA. It's a single event upset fault. And this fault is logged when FIFO status error bit indicates a SU event. And this again is an ARINC 429 cable fault most of the times when it's logged alone. A 3032 is logged if there are errors with serial communication status, like receiver overflow or a transmitter sync error or a receiver sync error. And this fault could lead to a reset of the main processor. And if this fault continues to exist, we recommend to check the ARINC 429 cable. And for these two fault codes, if the ARINC 429 cable continuity is satisfactory, then we recommend an RP replacement if necessary. This brings us to the end of by troubleshooting guidance, and we'll be summarizing these slides.
This webinar has presented a more clearly defined cause and suggested actions for key fault codes observed on the RP1 radar processor, which should lead to correct first removals of failed system components, which will lead to fewer unnecessary removals and will help you to reduce your operational costs and flight delays. We do have an associated service information letter, and that was released back in July, which gives additional details. And we've updated all of our line maintenance manuals, including one that's specific for our business jet operators. We've updated the operational byte code tables. We have listed in this webinar the installation guide and line maintenance manual for the 4000 for business jet and regional aircraft installation, and the document number for the service information letter that was released in July. And just for reference, there are two line maintenance manual installation guides for both Boeing and Boeing and Airbus aircraft as well. And then we also have some videos you can access. If you'd like to know more on how to access the LCD display on the RP1 and navigate using the two push buttons through its menu system, we have produced a video that's available on YouTube for that. And currently we do not have a specific business jet video because there's so many different business jets, but we have both a Boeing and an Airbus video, and the information in those videos the operational information is definitely applicable to all our business operators as well on how the system operates and hints on how to properly function.